In this lesson, we are going to talk about trigonometric identities. What exactly are identities are very simple. These are expressions on both sides of equal sign that they are always true no matter what the variable is. Give you one example. Let's say I have the following expression. X squared equal x times x minus 1 plus x. The two sides of the expression, they look different. Let's say x is equal to 0. If x is 0, then you get 0 squared, which is 0 is equal to 0 times 0 minus 1 plus 0, which is going to be 0. This means that this expression is true when x is equal to 0. When we assume x is 1, then we get 1 squared, which is going to be 1, and the right hand side will be 1 times 1 minus 1 plus 1, which is going to be 1 times 0 is going to be 1. You can see that for even x equal to 1, these two expressions are equal. Now, if you simplify this one, you're going to get x times x is going to be x squared minus x plus x, which is going to be exactly the same thing as x squared. This expression true no matter what the variable x is going to be. We say this expression to be an identity. Now consider another expression. Let's say we have x squared plus 1 is equal to x squared minus 2x plus 1. When x is equal to 0, then you get 0 squared, which is 0 plus 1 is 1, and the right hand side becomes 0 squared minus 2 times 0, which is 0, so 0 minus 0 is 0, plus 1, which is true. Now let's assume that x is 1. Then we say 1 squared plus 1 is going to give us 2, and 1 squared, which is 1, minus 2 times 1, which is 2, plus 1 is going to give us 0. And you can see that these two, 2 and 0, are not equal. So this expression is not always true. It's true for x equal to 0, but it's not true for x equal to 1. This is not an identity. In trig, we call an identity to be an expression that is true no matter what the angle is. This is what we call an identity. Now, there are some basic identities that we can assume they are always true. This assumption doesn't mean that we can prove that they are always true. For instance, the first one is Pythagorean identity, which says sine squared theta plus cos squared theta is equal to 1. This means that for any theta, this identity always true. If theta is 0 or theta is 35 degrees or theta is 90 degrees, any value for theta, this Pythagorean identity is always true. Another one which you can assume is always true is quotient identity. This means that sine theta over cos theta is always equal to tan theta. And another one is reciprocal identities, which says cosecant theta is 1 over sine theta, secant theta is 1 over cos theta, and cotan theta is 1 over tan theta. Now, the reciprocal identities, we just showed you in the previous video that this is our definition of writing 1 over sine theta. We are going to write cosecant theta. So these are just definitions. But the other ones, like Pythagorean identity and quotient identity, we can prove them to be always true. For instance, for Pythagorean identity, if you remember that sine theta of any angle is defined as y over r, and cos theta was defined as x over r. Now sine squared theta plus cos squared theta is y squared over r squared plus cos theta is x over r, so it's x squared over r squared. Now, since they have the same denominator, I can write this is equal to y squared plus x squared. But remember that in a circle of radius r, if this is angle theta and this is x and y, this is x and this is y, you can see with Pythagorean theorem x squared plus y squared is equal to r squared, which is the radius. So x squared plus y squared is really r squared over r squared, which is 1. So this Pythagorean identity, we just proved that they are going to simplify to 1. The other one is sine over theta over cos over theta. Sine theta is y over r over cos theta, which is x over r. Now this is y over r divided by x over r, which is the same as y over r times r over x. You can cross out r, you get y over x. But if you refer back to the circle, you can see that tan theta is opposite over adjacent, which is y over x, which is y over x. So this is equal to tan theta. So these two identities, we just showed that they are true, no matter what the theta is. And the reciprocal identity, these are just the definitions that we are using to define 1 over sine theta, 1 over cos theta, and 1 over tan theta. Now in this section, what you are going to do is that you have to show a given expression is either identity or not a trig identity. To prove that one, what you are going to do is that when you have an expression with the left hand side and the right hand side, we are going to simplify the left hand side until a point that we reach the right hand side. Then we say right and right are equal. Or we are going to simplify the right hand side until we get to left hand side. Then we say that these are equal, or at the same time we can work with the left hand side and the right hand side until we get to a point that left and right are going to be equal. Then we say that the identity holds. If there is no way we can go from left to right or right to left or both of them, then we say the identity doesn't hold. You may assume that this is very complicated, but in fact it's very simple. So let's do a couple of examples. The first example is to prove that tan squared theta plus 1 is equal to secant squared theta. No matter what the angle theta is, we have to prove that the square of the tan plus 1 is secant squared. We always start, in fact I always start with the side which is much more complicated. In this case, you can see that the left-hand side is a little bit more complicated. So I'm going to use one of those three identities, which I said the base identities, and you can assume that they are always true, and then simplify the left-hand side to get the right-hand side. I know that tan theta is sine over cos, so I can write sine squared theta over cos squared theta plus 1 I can write as 1 over 1. This is my left hand side. Now I'm going to start simplifying it. Since the denominators are not the same, I'm going to multiply this guy by cos squared theta. So I'm going to get sine squared theta over cos squared theta plus cos squared theta over cos squared theta. Now, since the denominators now are the same, I can add the numerators. So it's going to be sine squared theta plus cos squared theta over cos squared theta. Now, if you look at the numerator, this is really the Pythagorean identity. Sine squared plus cos squared is going to give me 1. So I'm going to get 1 over cos squared theta. I can write this one as 1 over cos theta, the whole thing squared. But 1 over cos theta is secant theta. So it's going to become secant squared theta. And you can see that we have reached the right hand side. So we can say that this is really a true identity. The next example is to prove that 1 minus cos squared theta is sine theta, cos theta, tan theta. Again, it's your choice. Either you simplify the left hand side or the right hand side, or both of them at the same time. I will pick the side which is more complicated and which has more terms. So I'm going to pick this side, the right hand side. So I'm going to write this one as sine theta times cos theta times tan theta. I'm going to write as sine theta over cos theta. Now, since this and this one can be cancelled out, I'm going to end up with sine squared theta. Now, if you remember, the Pythagorean identity says that sine squared theta plus cos squared theta is equal to 1. So I can move cos squared theta to the right. I get sine squared theta is 1 minus cos squared theta. Now, here I can replace sine squared theta, which is 1 minus cos squared theta, which is going to be the left hand side. So the identity is proof. The next example is sine theta over 1 plus cos theta. You have to prove that it's the same as 1 minus cos theta over sine theta. Remember, there are three ways we can prove an identity. Either you can simplify the left hand side and hopefully you get the right hand side, or you can simplify the right hand side, hopefully you can get the left hand side, or you can simplify both at the same time. Now we are assuming that, let's assume that this identity holds. What I'm going to do, I'm going to cross multiply. I'm going to say sine theta times sine theta and this one times that one. So I'm going to get sine theta times sine theta is sine squared theta, and I put a question mark because I have to prove that this question mark, this equal sign holds. So I'm going to get 1 plus cos theta times 1 minus cos theta. Again, question mark here. This is sine squared theta. The right hand side, I'm going to either multiply or use the formula. Just to multiply, just to show you what the end product is, 1 times 1 is 1, 1 times negative cos theta, I'm going to get negative cos theta. Cos theta times 1 gives me cos theta. Cos theta times negative cos theta gives me negative cos squared theta. Negative and positive, they cancel out. I'm going to get 1 minus cos squared theta. But remember the Pythagorean identity, sine squared theta plus cos squared theta is equal to 1. So I'm going to get 1 minus, if I move this one to the right, I get 1 minus cos squared theta is equal to sine squared theta. So I can replace this one with sine squared theta. And you can see that the left is equal to the right, so this is true. This is an identity.